that's worth like $50 and looks like a hearing aid battery, okay? But it really is gold. So, yeah, just don't take the precious gold coin, yeah? Good. So I was just talking to Professor Bolton about actually viewing the Bible. This is a fantastic resource for our university to have. And in order to, you have to know how to be careful, right? In the chemistry lab, you got to wear goggles, yes? Okay. Turning the pages of the St. John's Bible, the way, you don't have to wear goggles, all right? Because it's not going to leap out and contaminate you. If, you know, you can do a lot of things if you want to. But it'd be nice if you made sure that your hands were really clean, because biological things can be left behind from your filthy hands, if you get my drift, right? Now, chemicals are pure and godlike, but biology, ew. So really, they're trying to protect the Bible from being discolored, the beautiful white pages from being discolored by oils in your hands and all those yucky things.
So I'm gonna come back with some hand sanitizer, and I'm gonna, as discreetly as possible, set it over there on that counter.
By the fire extinguisher, maybe?
Yeah.
Okay.
After the session, if you want to go over and turn
Maybe right here.
John's Bible, we just ask you to wash your hands and
Yeah.
dry them as best you can first.
Right. Oh,
We're really
yay.
excited.
You're here. I'm happy.
Tomorrow, our second keynote talk at 12:30 in the Ralph Terry Forum is Father Michael Matella, who worked on the committee that was behind the St. John's Bible. He's coming from St. John's Abbey, so we're excited to have him on campus.
Great.
I will come back with some hand sanitizer.
Fantastic. Yeah, maybe down in the main office, they might have some. Okay, you can talk for a couple more minutes and then we'll start at 11:15. Pardon? Oh, yes. We're all about puns in this department. Yep, that's about the limit. Oh, so you do need to be connected. Oh, but you can have a separate connection. Okay, great. No?
It's the same thing.
Yeah, right.
A little bit. There, we'll just move it over.
Okay.
It'll work. And then when you get talking, I have to go over a few more things.
Okay.
We don't need that. That's the internet.
So what you need is this.
That's all I need.
So let's disconnect me and we'll just run you. Is that okay?
Sure.
I've already sent the gold foils around, and the gold coin is making the rounds. And I have the green laser pointer right here. Okay, perfect. Sure. Okay, so I'll take about 15-ish minutes and then I'll stall like song and dance, right? Yes. Total awkwardness. Okay. So this is focus, where we focus on something. What we're focusing on is right here in front of you. This is the St. John's Bible. And I am Dr. Baldwin. I'm the department chair for biology and chemistry. And I'm doing this talk. You'll notice whose name is first. It's not mine. So I'm the little lettering underneath. I'm Bruce Baldwin. And then Tom Kuntzleman is my colleague. And he's busy running around getting things set up for some demonstrations that he wants to do to help you appreciate the chemistry behind the gold that's on the pages that illumines the Scripture. And we're going to illuminate the Word. Ooh, 2 puns in 2 words. Illuminate the Word in the St. John's Bible. That's because they claim to use gold foil to illuminate the Word and to make it all fancy pants, right? That's my editing. I'm sure that when they come and make a presentation, they won't use the word fancy pants. So, a chemist's reflections on the St. John's Bible. And because I recently have had a sabbatical, I wrote a book on the chemistry behind the Bible. So my contribution to this talk is to talk to you about a portion of a chapter that I've written on metals found in the Bible. And guess what? Gold is one of the metals. And there's lots and lots of scriptures about gold in the Bible. So I'm going to start off and just, know that Dr. Kuntzleman is going to be a blur in the background because he's running all over the place and doing things. Good, it worked. So, where in the Bible is gold found? Well, obviously, as we open the St. John's Bible, you can find out that, oh, look, there's gold in Luke. Because right there, see, it's gold. Okay, well, all right. But I'm talking about here, where is gold referenced? Because gold didn't just drop out of the air only for us modern people. Gold has actually been known for many, many centuries. It's talked about in Genesis in terms of guys that were especially gifted in working with gold, making everything from jewelry to temple ornamentation, all that stuff. Somebody had to have the knowledge to figure out how to do all that fine work. And we have actual references, especially in Genesis, to people who are particularly skilled at that kind of work. Exodus actually gives us some information on the types of gold articles that were used in the temple and in the tabernacle to worship God by the Israelites. And then there's a great story in 1 Kings that I'm going to spend a little time on because I think there's a chemistry behind the story that I have never heard talked about before. And it's based on some research that I did last spring for my sabbatical that has turned out this book that's not published yet, not available, and you're just going to have to be patient. If that's something you have to have before you die, if that's on your bucket list, then you're just going to have to wait. But we'll talk about these things, especially the 1 Kings story. So, what makes gold special? We have this really funky looking table over here, and it has on it most of the representations of the fundamental elementary elements of the universe listed on it. They're all there. Everything that makes up stuff in the universe is on this table. And even we're finding newer and newer and newer parts of that table. Livermorium over here at 116 is one of the newest elements on the periodic chart. It really doesn't matter very much. It's not nearly as important as you might think because it only exists for nanoseconds at a time. That's not enough time for you to do a 3-hour laboratory. Okay? The times don't overlap. So, what of all the elements that are on this periodic chart, what makes gold so interesting? Well, part of that answer has to do with history, and part of that answer has to do with a chemist's understanding of gold. First of all, gold is malleable. That means that gold can be pounded into very, very thin sheets. In fact, so thin that you can actually see through it. It is possible to pound gold that thinly, and it will still be like a sheet. Now, the foils that you saw are not thin enough to actually be see-through, but they're more like very fine tissue paper than they are like a piece of aluminum foil, for instance. So gold has that ability to lay flat and to be worked into a coherent piece that could cover something. That's going to come back in just a moment. Unlike most of the other metals, there are lots of metals on the periodic chart, and if you look here, basically in this center portion of the periodic chart, we're in the rich metalloid zone of the chart, and what I'd like to draw your attention to is the AU at the bottom of the periodic chart. That's how we represent gold on the periodic chart. Gold, unlike all the other elements that are in this section, is not only malleable, but also ductile. So it can be drawn out into threads, and that characteristic is also going to come back in just a few slides. We're going to talk about that. Gold is one of the coinage metals, and now we finally get to talking a little bit about the structure of the periodic chart and how the elements are represented. Group 11 is often called the coinage metal group. Why, you might ask? Well, because there's gold, there's silver, and there's copper. Those three metals are coinage metals. They've been used in coins since antiquity. So archaeologists have found gold coins, they've found silver coins, and they've found even copper coins, even dating back to before the time of Christ. So we know that those metals have existed for a long time, and therefore you might think that there might be some words associated with them. But something I want to bring to your attention is that I've just pointed out to you that AU represents gold. Does anybody see a more intuitive two-letter representation for gold somewhere up on the periodic chart? Can you tell me what number above that element? What number is it that looks like it should be gold? 60 what? 64, right? Gold. If we use our elementary education cap, our thinking cap from days gone by, gold sounds like it should be GD. Did I get it wrong? Is this really not the coinage metals and I'm just blowing smoke on you? Because obviously GD is in a different part of the chart. What about, can anybody find SI? Because that's where silver should be, right? Where's SI? What number is it? 14. Oh my goodness. Talk about different parts on the periodic chart. Can anybody find CO for copper? Oh, right there. Yeah, somebody said something because they know too much. I heard it. Okay, so the periodic chart is representing the fundamental building blocks of the universe. And we have obviously many different types of building blocks. And something you need to know about the chemistry behind the periodic table, in fact, the chemistry behind gold, which is what the rest of this conversation is going to be about today, has to do with the age or the antiquity of our knowledge of the coinage metals. It used to be that people didn't speak English to each other. What language, way, way back, do you think they might have talked to us? Oh, Latin. That's the home run. Because once you understand that because those coinage metals have existed for a long time, maybe when people first thought up the elemental symbols for the elements on the periodic chart, they might have been thinking in Latin, or at least referencing words that were Latin-based. So now, if we use that background, it's much easier to understand that AU comes from the Latin word aurum, and that is how Latin speakers talk about gold. AG, does anybody know the Latin word for that? Argentum, good. Argentina, has anybody put that together before? There's a lot of silver mines in Argentina. That's why it's called Argentina. And then, does anybody know the Latin word for copper? Cuprum, or cuprous, Cu. So now it starts to make sense. And in fact, the other elemental symbols, Co actually describes cobalt, because everybody decided that's what they wanted to do. And Si is not silver, but silicon. And GD is one of my favorites. That's gadolinium. Gadolinium is what makes it possible to get MRI of cancerous tissue. So there's a real use for it. It's a little bit more than just, oh, I know what GD means, and I'm better than you, right? Okay, so my point in talking about that is if you understand the chemistry behind the periodic table and the history behind the periodic table, it suddenly makes sense why things are represented the way they are. And there's a similar story about mercury. Okay, so it's used, that kind of thing comes up a lot. So, what else can we find out about gold? Well, let's talk about its malleability. This is a very, very awkward picture that I took myself. It doesn't illustrate things very well, but what I was trying to illustrate is that the gold foil will actually form to the shape of the thing that's underneath it. If you have significantly more skill than I or Dr. Kuntzleman have. So if any of you are like goldsmiths and you want to coat a penny with gold foil, go for it. But we didn't have you available to us yesterday when we were doing this. So basically we touched it too many times, and now it doesn't look like you can see Lincoln's head underneath the gold foil. You could when we first put it on, and then naturally I didn't have my camera ready. So anyway, why would you want to hammer out sheets? Well, to follow the directions of God, basically, because the altars and a lot of wooden pieces needed to be coated with thin sheets of gold. Why? Because God told the Israelites to do it. And they didn't question God, they just did it. And it turned out they could do it with gold, but you can't do it so easily with silver or with copper. Actually, this job can be done with those other metals, but gold is especially good at this job. Gold being able to be pounded out into flat pieces also lends itself to making wonderful jewelry, and the Egyptians were really good at that. And the Egyptians gave a nice going away present for all the Israelites, right? They were really happy to see the backside of the Israelites. Remember that? After all the plagues and stuff. Please go. Take my gold. Please go. Get out of here, because we don't want you anymore around us. And it's also great for making into coins, which are flat objects. So gold is well suited for that type of application. In contrast to other metals, gold is also ductile. This is the ink cartridge ribbon from an HP inkjet printer cartridge. And if you look at it carefully, you might notice a bunch of lines. Those are all tiny individual threads of gold. Gold is able to do that. And if you are a scrapper, you already know that there is gold on a lot of electronics materials, and HP inkjet cartridges have the gold out so it's visible. And so there it is. You can also see the malleable portions, because those are thin film objects or squares. Those are also made of gold. So there is gold. You're not going to get rich from this inkjet cartridge thing, but maybe if you had 100 of them, you could make some moolah, right? Okay. Why is ductility so important? Because again, God commanded that threads of gold be entwined with the other woven materials like wool and linen that were commanded to be part of the temple curtains. And if gold wasn't going to make nice, long, draw-outable threads that could be skillfully woven in with the other materials, then you couldn't follow God's commandment, could you? And our God does not require outrageous things of us because He designed the universe. He has figured all this stuff out. So gold threads works quite well. Other metals get all crumbly. Like I'm glad God didn't say to put sodium metal into the threads of the temple, because then it would have lit on fire. Because as we may see a little bit later in the demo today, sodium starts on fire when you let it interact with oxygen sources. The threads were also woven into the priestly clothing and into the ephod. So again, it's got to be ductile. And wires are often used to hold precious stones into crowns, and again, the priestly vestments and all that stuff. So malleability and ductility are a unique combination of characteristics that gold has that other metals don't have, like lead. Lead is malleable, but you can't draw threads of lead. And lead is another metal that's mentioned in the Bible. So now we get to that first king story. This is great. Put on your Sunday school hat. Pretend you're back in time. All right. Rehoboam's gold shields. Notice I put gold in quotation marks. This is my interpretation of what Rehoboam did in response to awful things happening to him. He had a tough life. So Solomon, greatest king in all the world, in all history, right, has these gold shields. The splendor of Solomon's kingdom is reflected, pun intended, in the gold shields being displayed behind him at all public appearances, right? Especially in the setting sun. Can you imagine the majesty of all that light reflecting off of those gold shields? Awesome! Solomon, awesome. Solomon kicks off and he goes to join Jesus. That's great. And then Rehoboam comes to power. Rehoboam is Solomon's son. Rehoboam has some problems, if you remember some of the stories there. Like people are in open rebellion against him. They don't like him. He makes some unfortunate decisions with young people as his advisors. There's a lesson in there, right? And along comes another king, Shishak of Egypt. And he comes in and beats the snot out of all of Rehoboam's guys and takes the golden shields of Solomon. So they're all gone. What is Rehoboam, boy, quotation marks, king of Israel to do? How can he maintain the glory when he comes out to deliver his public address? How is he going to reflect all that light? Oh my goodness, what's he going to do? This is what I think he might have done. In the Bible, it actually says that Rehoboam made bronze shields. That's why there's this right underneath it. So this is gold foil up here in the Petri dish, which you had an opportunity to look at before. This is native copper collected in the UP by Dr. Gibbs, the same Dr. Gibbs who this building is named after, Whiteman Gibbs, that Gibbs. He actually found this piece, as I understand it, up in the UP and brought it back, and it's in our collection, and it's used in the geology course and the earth science course as an example of native copper. It's funny, the UP is one of the few places in the world where native copper that you can actually see as metallic copper is found. You didn't really have that available to you very much in the Middle East. But what Rehoboam did have was he had a lot of copper left over from Daddy's conquests. So Rehoboam does not have very much gold, but he has a ton of copper, probably literally. So what's he going to do? Well, what he does is he makes shields out of copper or out of bronze. And the funny thing about the way the Hebrew word and even the Greek words for copper things is all the same thing. So whether a person in those countries, in those times, is talking about copper metal or an alloy like brass or even bronze, which is a different alloy, they use the same word. So the authors of those books, especially Genesis and Exodus, would not have thought it important to differentiate between the three things. But can you imagine making shiny copper shields out of native copper that looked brown? That's not going to reflect the glory of anything. In fact, it's going to be very embarrassing. So I did some reading in the Journal of Chemical Education, and I went way back, like into the 40s. And there was an article, an experiment, about purifying copper, cleaning it up, and then allowing it to cool down. You superheat it, and then you allow it to cool down in a special atmosphere. And it actually looks golden in color. I did this experiment, and that's the result. Contrast the gold here with the part of the copper foil that was not treated that way. This is what you might think of in terms of bronze, but that sure looks gold, doesn't it? All I did, and maybe this is what Rehoboam's advisors and magicians were able to do, is I heated the copper piece with a torch, got it red hot, and then I put it into an atmosphere of a solvent that provides electrons. That's as deep as I want to go with this audience. It shot a lot of electrons onto the surface of the copper as the copper piece cooled down. Then once it got to room temperature, all of the surface copper atoms were really pure copper atoms. And if you do that cleverly and well enough, it took me a few tries, you get this nice gold color. So it's possible that Rehoboam's people were able to replicate this experiment with materials that they had available to them. I imagine ethanol could have done the same thing. And I'm sure there was plenty of wine in the king's storehouses, right? So they had the ability to do this. Whether they did it or not, I don't know. There are other things like brass that really do look gold, right? But they're not gold. And actually, this is going to come about in our talk as we develop it for you guys. So there is a way to treat copper so that it looks like gold. I think maybe this is how we came up with Rehoboam's gold shields. It's a possible explanation. Is it the only one? Well, for one thing, there's no way to know, because I can't do time travel. I sure wish I could. That'd be fun, to go back and see Rehoboam arrayed in front of his copper or bronze-colored shields, and then to get behind it without being executed to find out how it was done, because people usually didn't survive once they knew secrets like that. So anyway, that's what I think might have happened. It's really important. It actually says in the scripture that the captains of the guard appeared with the shields, and then as soon as the king retired from his talk, they put the shields away. So the shields were only out in the air, which has oxygen, and would have discolored the copper even if it was treated, and coat it with black copper oxide or with red copper oxide, and turn it more into that tarnished look that you could see at the previous picture of the gold-colored copper piece. And then at the upper end, it was kind of more like bronze that you would see on a bronze statue. So I'll bet they had to redo this if this is the method that they used. And if it was viewed in low light, which would have happened towards the end of the day, maybe you would be deceived into thinking, oh, Rehoboam is all that. He's as good as Daddy. So, of course, I'm going to stay with Judah, and I'm not going to go with those icky other 10 tribes, right? So maybe that's what was going on. And now it's time for the handoff. The tag team has begun.
Okay. So what I was trying to do in connection with the St. John's Bible is I was interested, as soon as I saw it, the first time I saw the St. John's Bible, I was immediately drawn to the gold illuminations. They're just beautiful. And I started immediately thinking about the chemistry of gold and some of the physics of gold as well. And so I thought, oh, well, I wanted to think about what are some of the properties of gold that make it a really good choice for the illuminations. And Dr. Baldwin actually suggested to me an experiment, and I thought, no, we can't do that. That's not going to work. And as I reflected upon his suggestion a little more, I thought, well, let's just try it and see what happens. And that's sort of what this part of the talk's about. I think, what time does this end? 12:15. All right. Well, we'll see how far we get. If I don't get through everything that I have planned, I'll just modify things a little bit for the next talk and do some different experiments for the next round. But anyway, let's explore some of these properties of gold. One thing that makes gold a great choice for the Illuminations is that it is really unreactive. It does not I mean, you can throw just about anything you want at gold, and it's not going to react. And what this list here, this list of elements, they're all metals. All the elements that you see on here are all metals. And there's something we use in chemistry called the reduction potential. That's a measure of how reactive a metal is. And on this list, at the top are going to be your most reactive metals. And at the bottom, we see gold and platinum. Those are very unreactive metals. Now, it's one thing to talk about the reactivity of substances. It's quite another to actually see this. And so what I want to do is I would just want to show you the differences in reactivities of these sort of things. Because when I see this, I see a whole bunch of possibilities for experiments. So let me just show you the first one here. What I'm going to do is I'm going to take a little bit of calcium metal. Now, this is not something you're going to find outside on the sidewalk. Calcium metal has to be prepared specially from compounds that contain calcium. And what I'm going to do is I'm just going to add a little bit of calcium to some water and watch what happens. So we can think, actually, we chemists, we sometimes think of water as an acid. Sometimes it's a base. But in this context, we're going to think of it like an acid. And you probably can guess it's not a very good one. It's a pretty weak acid. And it is, in fact. And so what I'm basically going to be doing with this, I'm going to be looking at the reactivity of these metals with acids of different strength. So water is, it's just not a very good reactive acid. Take a little lump of calcium here, and we're going to pop it in the water, and we're going to watch what happens. And I immediately see some bubbling, which tells me that the calcium, it reacts with water. So obviously a metal that reacts with water, that's not going to be a good choice to put in your Illuminations. Oh, it's really going now, isn't it? It's getting hot. You might see a little bit of white solid formation. That's because the calcium is forming a salt. And when calcium forms salts, they tend to be white in color. And that probably makes sense. Calcium's in milk and milk's white. Calcium's in bones and teeth, and your bones and teeth are white as well. But that, boy, that's really hot, isn't it? I'll have to use more water next time. But that gives you an idea of the reactivity of calcium. And if you look at the chart, anything above calcium on that chart will also react with water. Okay? And actually, we can go as far down as sodium. Sodium will also react with water. So anything sodium above is going to react with water. You get to magnesium, you can get magnesium to react with water, but you got to get the water really hot, or the magnesium really hot. But generally, magnesium does not react with water. But it does react with a slightly stronger acid, actually quite a bit stronger of an acid. This is like, say I do the math in my head, it's like 100 billion times stronger of an acid, okay? We're going to use some hydrochloric acid, which is 100 billion times stronger. And if we use that, we can kick magnesium hard enough to get magnesium to react. So I just got a little strip here of some magnesium metal. We're going to take that magnesium metal. We're going to place it in our test tube. I'm going to add some acid. And actually, anything on that list with a negative number, a negative reduction potential, will react with hydrochloric acid, basically. I'll pour it in there. Oh, there it goes. Off it goes. That's what I mean by reactivity, okay? This is reacting with an acid pretty vigorously. Woo! Smell a little bit of the acid, a little bit of acid vapor going on there. Getting a little hot. Put that down in here. I probably should have used zinc. I'll remember that for next time. Whew. Smell all those vapors? A little bit? Just a little bit. Chemistry stinks sometimes. All right. I want to show you the reactivity of, some of these things will react with oxygen in the air. Like we know that iron, well, that rusts, right? What's going on when iron rusts? It reacts with oxygen in the air. Well, I like to speed this reaction up. It's kind of fun to do that, so you can see it happen sort of in real time. So I'm just going to take some steel wool here. I don't think I'm going to get to this experiment, so I'm going to just move this. Put this down here. Make sure my calcium's out of the way. So steel wool, steel is basically iron. It's pretty much almost all iron. So I'm just going to take a little bit of this steel wool, and I'm going to line the inside of this beaker with the steel wool. All right? And then what I'm going to do is I'm going to light that on fire. And when I light it on fire, it's going to react with the air. But I want to speed things up a little bit, so I'm going to push a bunch of fresh air on it really quickly. I can do that with this, right? I think I can. Yeah. This is blowing fresh air onto me right now. I'm going to do it onto this. If I have my lighter, we can see rusting happen really fast. That's kind of pretty, isn't it? Here's an interesting question to think about. If I took the mass of that steel wool prior to the experiment, and I took the mass of the steel wool now, you think its mass is greater now or before the experiment? It's interesting that the mass of that steel wool is greater now because oxygen from the atmosphere has chemically combined with the iron. It's stuck to it chemically. And those oxygen atoms, when it sticks there, well, oxygen atoms have mass. And so if you do a careful experiment, if I do this carefully enough, even though I see some sparks fly off, which represents mass flying off, if I measured the mass of this after the reaction, you would see an increase in mass. I've done this many times, and it always undergoes an increase in mass. So I see that, and actually, I know that mercury and above, any of these elements, will react with oxygen in the air given enough time. It'll do it. Gold's not going to. You got a shiny piece of gold, it's sitting on the floor, basically come back a million years later, and it's shining just as bright for you. It just does not want to react with stuff, which makes it a great choice for the illuminations. You stick them in there, and it's not going to react with water in the atmosphere. It's not going to react with any acids that can get in the atmosphere. There are gases that will dissolve in water, in rainwater, and it will make that rainwater slightly acidic. Carbon dioxide, when it dissolves in water, makes the water slightly acid. So it's good to have a metal in the illuminations that's not going to tarnish or rust or react with any substances anywhere. So gold's a beautiful choice for that. And I think here I have an old, I think I do. I have an old candlestick. This is silver. All right, you can see it doesn't have quite the shininess that the bottom has. There was a little protective coat here that I took off. You can see the bottom, which has been protected from the atmosphere, is much shinier because there's stuff, usually sulfides, sulfur-containing gases, will react with the silver and tarnish it in this particular manner. And you can do some chemistry to take this off, and you drop by the lab, I'll show you how to do it. It's not that hard. Something you can do at home pretty easily. The coinage metals, all of them they're fairly unreactive. All the coinage metals. Dr. Baldwin mentioned the copper, the silver, and the gold. They're good choices for metals, for coins, because they generally don't react. However, if you kick copper hard enough and you kick silver hard enough, you can get them to react. You can. But it's really difficult to get gold to react. And I want to show you this. I want to show you this here. You don't happen to know the pKa of nitric acid, do you? Off the top of your head? HCl, we call that one like 1 or 10, depending on the concentration. Is it? Negative 1.3? How about hydrochloric? Negative 7, so you're right. That's interesting. I wouldn't have expected that. Anyway, what I'm going to do here is I'm going to try to take these different coinage metals, copper, silver, and gold, and I'm going to see if I can't get them to react with, you can't get them to react with hydrochloric acid, but you can get them to react with nitric acid. So I'm going to just try to do that here real quick. I'm just getting this set up here so you can see what I'm doing. I don't want to do this on the large scale because I don't want to kill myself. All right, let's see what we got here. Let's see if my ladybug will wake up. So you can see what's happening. Okay. So what I'm going to do here is I'm going to take some concentrated nitric acid, and I'm going to take some whey boats here, and we're going to add this concentrated nitric acid to some copper and some silver and some gold and see if I can't push these metals hard enough to react. Let's just see. Where's my metal samples? Here's some copper. Excuse me, sorry about this. We're doing time-wise, I got 20 minutes. Here's my silver. Okay. Just lay a little piece of copper in there. Did I bring a scissors? Yes, I did. I thought I did. That's going to make things a lot easier. I can't tell which way to move the thing. Everything's backwards. Okay. Now the gas that's going to be released is toxic, but one thing you have to remember in chemistry, that it is the dose that matters. Okay? It's the dose that matters. So often you're going to see, well, water's toxic if you drink enough of it quick enough, okay? So I will be producing a toxic gas here, but the dose will be well below what I'm able to handle. So I won't be killing myself, or you if you can smell it. Just add one little drop here. See some color? You see some green? I think that's enough. You see that brown gas that's being produced? That's nitrogen oxides. Very similar, if not identical, to the same type of brown color you see in smog. Okay? When cars burn gasoline, they produce a little bit of nitrogen oxides. They produce that smog. Now, I don't know if you can see, but that's a blue color there. And that blue color tells me that the copper metal has reacted and it's become copper ion. It's in a sense you can call it like rusted copper, in a sense. Okay? It is now copper that has been oxidized. And that's going to be a change that, we don't want to see if we're going to stick copper illuminations in a Bible, that there are nitrogen oxides that get released in the atmosphere. And that could potentially change our illuminations if we're going to leave it set for, 1,000 years. They want this thing lasting a long time. Let's do the same thing with silver. Where's my silver? There it is. See what happens when we do this with silver. Piece of silver. Nice shiny piece of silver. Boy, that's an expensive experiment. Put a little bit of nitric acid on there, really push this thing, trying to get it to go. Add a little bit of that. See discoloration immediately. Do you see it? Okay, good. that's already reacting. All right? So probably not going to want to put silver in the illuminations either. Over a very long period of time, some materials in the atmosphere could probably mess with this. Try the same thing with gold. No, I better not do that. I might get in trouble. There's our gold. Now this is concentrated nitric acid I'm adding. I add this to my hand, it's going to turn brown pretty quickly. All right, it reacts with stuff really easily. Just put it on my gold there, and ain't nothing happening, nothing at all. It's just sitting there, no bubbles. It's just resistant. It is very, very resistant to chemical corrosion any way, shape, or form. So it's a great choice to stick in our illuminations here. Let's put you back on the card. All right. I do this old-fashioned way. Okay, here we go. The other part about gold, I think, that makes it a great choice for the illuminations, is it's got this beautiful yellow color, right? I mean, gold, if you look at this table, you know, anything that's colored black is a metal. These are blue. Your eye may not pick that up. So these are blue. They don't count. But anything on there that's black is a metal. And there's two elements on the table that are yellow. Gold's one, cesium is the other. The cesium is way too reactive to do anything with. It's way too reactive. Really, only copper, which is orange-red, and gold are the only two that you can do anything with that have a different color than silvery. Some have shades of other colors, but you know, you look at it, unless you're like trying to really see the color, it looks silvery to folks. So of course you want to use this, you know, come on, it looks beautiful. Do you see that golden color sitting there in the illuminations? And the way the light comes off, it makes all those pictures just look fantastic. So Baldwin had this idea. He's like, he knows these machines that I have, and he's like, why don't you use your ocean optic spectrometer, that's this thing right here, to try to see if we can't test whether it really is gold that they stuck in there. And I thought he was crazy, but then I thought about it a little more, and I thought, you know, maybe it will work. Let's just try and see. Let's just try and see. So we're going to try to use gold's property of this beautiful yellow color to try to see if it really is present in the illuminations. Before I do that, I would like to talk to you a little bit about the properties of light, because you know, we used light. We basically reflected light off of these pictures, and then collected the light that was reflected. So I'm going to just talk to you a little bit about why things have a particular color. Basically, if you have a white light source, much like these lights up here, they're basically a white light source. All of the colors of light that you can see are in that white light. Now it doesn't look like it, because when you add them all together, the light looks white. But if you could analyze that, which I'm going to do right now, you can see if I can get my spectrometer going here. Get you going. This thing measures the light coming off of any source. It measures how much light at different wavelengths is being given off by something. Another way of saying that is this measures how much light of different colors is coming off of something. So we get this, come on baby. There we go. There's my spectrometer. I'm going to point it up there at that light. And let me just change this just a bit, and it'll help out. 250. That's going to help a little bit. You see that little hump there? See that? That hump goes in between about 400, maybe 450, and 800. You see that on the bottom where it says wavelength nanometers? That big hump there tells me that light that I'm pointing it at is giving off light somewhere in between 400 and 800 nanometers. And you know, when you use this stuff enough, you remember really well that red light, that's down around 700. And that goes red, orange, yellow, green, blue, violet, and violet's down around 400. I like this laser here. Let's just play around with this laser a second. Oh, wrong way. You see that green light coming off? See that big band in the middle, about 540 nanometers? That's green light. Okay, that came from this laser. I was just pointing this at the green laser. All right? So each wavelength corresponds to a particular color. It's a good thing to remember. All right, let's get back to this. We're just going to do it this way because the color an object appears is going to depend upon the light that gets reflected off of it. So this thing looks red because white light, I like to say white light has Roy G. Biv in it. Red, orange, yellow, green, blue, indigo, and violet light. So Roy G. Biv shines down onto this thing, and basically red bounces off. Red gets reflected. So red gets reflected off and into my eye. That's why that thing looks red. Now, it's more complicated than that. It's a little more complicated than that because really what's going on, the color an object appears, if you look down here on the bottom, that's going to depend upon the colors of light that get absorbed. So it really kind of works like this. When light shines on that guy right there, green gets absorbed because green, it just uses a colorway here. Green is opposite red. So green's opposite red. And pretty much all these other colors here, to a sense, get reflected. And when you add all those other colors up, it looks red to your eye. That's what it's going to look like. I mean, that can be happening too. So we tried this with, I don't know if I'm going to get to that. We tried this with the Illuminations. I don't know, I may be able to do it right now. I mean, you just take this, you shine a really bright light on this, and you just take the fiber optic and you just measure the light that's coming off. And we did this with, we bought a piece of gold coin, a real tiny one. Didn't you send it around, the gold coin, or no? Okay. Somebody stole my gold coin. That's $50 you owe me. Cost me $50 for that little thing. But we just shine the light on it. So this down here, I've got this here to guide you. So these wavelengths, this little bar here tells me about 550. That's going to be green light. 525 is going to be green. 650 is going to be red. So when you shine light onto gold, as far as in the measurements we were taking, you get some blue and some yellow, some blue and violet that comes out, but not much. And then when you get up into the green and the yellow and the red, you get quite a bit of light reflected. So what you're seeing when you see gold, you're seeing the sum of green light, yellow light, a little bit of orange, and some red. And to your eye, that looks golden. Now that may sound funny. You got all this red light, you got all this green light. How in the world does that look yellow together? Well, let me show you how this works.
This is cool.
Let's try this.
I got it.
Well, it's subtle. It is subtle. All right, that's blinking red, right? What else do I got? How come that one won't go off? There we go. This one's blinking green, yeah? I'm going to stick them together. Remember, we got a lot of green light, we got a red light. We're okay that yellow is yellow, but how in the world is red and green yellow? Well, you stick them together. Look there in the middle. You see where the two lights combine? What color does that look like? That looks yellow. So, of course, gold is yellow because you're taking green light and red light and you're adding it together in a nice yellow color, and, of course, the yellow-orange color, that looks yellow. So that's why gold is going to look yellow. All right, what happened when we did this with some other stuff? The gold foil is 23 karat gold. What does that mean? Well, the 99.99% gold, that's 24 karat gold. The 23 karat gold, that just is 23 divided by 24, whatever that comes out to. That percentage of that is gold. So 23 over 24, I don't know what that come out to, 90-some percent? It's up there, 95-ish, somewhere in that neighborhood. So I tried the same experiment with some 23 karat gold foil. Hey, we get something that's pretty much the same. And I want to tell you that this is shifted just a little bit towards copper, what copper looks like. And usually the other metals that are added to gold to give the lower carats, usually copper is what's added. So it makes sense to me that this is shifted a little bit towards what I see for copper. We tried the same thing with some gold sputter. There's some material we use in a electron microscope. It's a gold sputter, and we tested that, and it's shifted a little bit towards the copper, but I just think that's because the gold was sputtered onto a piece of copper, and some of the gold had rubbed off. So I think that's why I'm seeing a little difference between these two. I tried it with some 18 karat gold plated jewelry I bought at Walmart. That was only 15 bucks. This is a gold coin that Dr. Baldwin had. I don't think it's pure gold, but nevertheless, it shows that the spectrum that I'm looking at is characteristic of what I see for the pure gold. I tried this with some different metals. I tried it with copper, and we see a very big difference in copper. So if I see this kind of shift, I know that I'm probably not looking at gold. I'm just trying to give you an idea of how big of a shift you might see with metals other than gold is all I'm doing here. And if we look at the light that's reflected in copper, it's basically yellow, orange, and red. Hey, copper looks kind of reddish, doesn't it? So this should make sense. This is silver. I tried it, like try any element up there you want to. They're all silvery in color, right? So I did this with aluminum. I tried some platinum. All the silvery ones look like this. They basically reflect all of the light, pretty much all of it, which is why they look silvery. So, silver is kind of a whitish color when it comes to metals. Tried some brass, because I thought, maybe they're cheating. Maybe they're taking something that looks like gold, but isn't. The one thing that comes right to my mind, use brass. Brass is a great way to make people think they have gold when it's not, and they didn't fool me with my method, okay? I can see a big difference between what brass looks like and what the gold looks like. So then we decided, okay, we're going to try some of the illuminations here. And this is what we saw. You're looking at the same thing that I saw. So there's a picture of the illumination. Okay, that's a picture of the one we used. I tried to, if you look at the cross, that's the area that I looked at. I tried to pick versions that had really large, bold regions of gold. So I got some nice reflection. This was from Mark chapter 9. You see that picture of the transfiguration of Christ. I also did the illumination in Luke 1, which is the Bible's open to right now. There's a huge band of gold right down the middle. That one was easy to collect. And I also took the picture in Acts 5. I don't know what's going on there. I don't know. I have to have one of the theology guys tell me, I guess. But if you notice, it doesn't look exactly like the pure gold. And really the way I did this is first I took Dr. Baldwin's gold coin. We didn't really know if it was gold or not. And then I'm measuring these spectra and trying to see if they match up, and they weren't. And I was like, wow, the method doesn't work. Well, it's because I didn't do my controls, is why. I didn't really take the spectrum of the pure gold. And so I took the spectrum of the pure gold, I started to take spectra of other pieces of gold, and when I saw all of those really matching each other well, that gave me confidence that what I was seeing here was real. Okay? So what I'm seeing here is some reflectance that looks like gold, but it's not pure gold. And as I reflected on my results a little more, I realized that when they are adding these illuminations to the manuscript, they're doing all sorts of stuff to it, right? I mean, I don't know. I'm not an artist, right? I don't know what gesso is, but they made some gesso and they stuck it on there with that. So in the chemist's mind, they put a bunch of dirt, crap, and corruption in there. That's messing up the spectrum. But nevertheless, it looks to me like they really did use gold. It's just been perturbed a little bit. Okay. I think that's probably a good place to leave off for now. I want to make sure I thank some folks were very helpful in this in studying here. Robbie Bolton for lugging this Bible over. He wouldn't let me put it in the book drop when I was done with it, though. He said I had to actually bring it in the library. Karen Parsons helped me out with with some things, and Liz Brueggemann and Sarah Boyer, who helped set up a bunch of the experiments. Thank you for your attention.